HO. There is evidence. Whenever you reject, you say there is evidence. When you fail to reject, there's not enough evidence of HA. Any others from 7.4 or 7.3?
7.3, number 28.
28, okay. So this is t-testing. We have to use degrees of freedom and find the t critical value. Unless we use the calculator, we don't necessarily need to do that. Oh, and I wanted to mention that as well. In part B, well, part A says to write the hypothesis in words and symbols. In part B, it says find the critical value. And then draw the rejection region. Again, I used to be a stickler with that, but if we can find the p-value, why do we need to find the critical value also? It's doing the same thing twice. It's doing the same thing twice. Okay, so I'm not going to do the same thing twice. I'm just going to do it one time. I'm going to find the p-value, and I'm going to make my decision to reject or fail to reject. So I'm encouraging you to skip that, finding critical values, and follow the three-step process. If you follow the three-step process, you'll get to the correct solution. You get to the correct answer to the question based on the p-value. Because the rejection region will give us the same thing. Okay. If we use this process, I don't need to do the A, B, C, D, E, F, G, H, I, J, all the steps. Okay. You don't need to write out part A, part B, part C. You just do the three-step process, state the question, answer the question is the ultimate goal. So 22, you said?
28.
28, okay. 7.3. Number 28. The dean estimates that the mean number of classroom hours per week for full-time faculty is 11. A member of the council wants to test this claim. Sample of classroom hours for 8 full-time faculty were 1 week is shown in the table at the left. Can you reject the dean's claim? All right, so there's no greater than or less than. So this is an equals and not equals. Faculty are working 11 hours per week. So that's the question. Do faculty work? And from our sample, notice I'm not looking at the data yet. Okay, so the data will tell me if faculty are actually working 11 hours a week, if they're working less than 11 hours, or they're working more than 11 hours. So I'm going to write my HO and HA. This is step 1, the 3-step process. So I'm talking about a mean. The mean is 11 hours, not a proportion. I don't have a less than or greater than, so I'm just going to do it equals and not equals. The mean is either 11 hours or it's not 11 hours. If I get my data and I get 10.9 hours, statistically there's no difference. 11.3 hours and 11. Statistically, there's really no difference between those two numbers. So what constitutes the difference? That's about 2 deviations away from the mean. That's what z-score will give us. And that's what we did in chapter 5. So I got to take the data and I'm going to find the sample mean and sample standard deviation. So I can do my z calculation. I'm just going to enter that data into a list. List 1, probably the best. Classroom hours, 11.8, 8.6, 12.6, 7.9, 6.4, 10.4, 13.6, 9.1. When I enter data, one of the more common mistakes when you're doing a t-test and you have data or even a z-test, people enter the data incorrectly. So I had a couple people make that mistake on the quiz that we had where I gave you data. So make sure you're entering data. I look at the number, I enter it, and then I look at it to verify that I entered the correct number. A lot of times people forget a decimal place, 7.9, they end up typing 79. That'll give you the wrong z-score, that'll give you the wrong p-value. And that ruins everything, right? Just because you hit the wrong button. So double check when you're entering data. That's a small piece of advice. I'm going to find you don't have to do this because you could just do a t-test on your calculator, but I'm going to show the mean of the sample is 10.05. I'm going to do the t-test 10.05 minus 11 S 2.48. And I forget how many sample sizes, 9? No, 8 faculty. Okay. So we're comparing these two numbers ultimately, 10.05 and 11. Is there a big difference between those two numbers? Or is there no difference between those two numbers? That's what Z-score comes up with. And T-score. So this is just a straight t-test. I have data. My data is in list 1. The population mean is 11. And I choose not equals. This is called a two-tailed test. -1. Okay, just by getting that T statistic, I'm pretty sure there's really no difference between 10 and 11. Faculty are supposed to work 11 hours a week. I got a sample with 10 hours a week. Really, there's no difference between 10 and 11 from that T statistic. I got a p-value of 0.315. So then we make our decision, our rejection decision. We're going to fail to reject. P-value is greater than 0.05. This says alpha is 0.01, so I would say it's still the same thing. The p-value is greater than 0.01. Therefore, I would fail to reject. There's not enough evidence. There's not enough evidence. I'm going to use the word different. This means that the two things are different. This means no difference. There's not enough evidence of HA. There's not enough evidence that 10 is different than 11. There's not enough evidence that faculty are working something different than 11 hours. Now the wording is a little tricky. I mean, you could ultimately say there's, some people will say accept this, some teachers will teach this, and I know I did early in my career. If the answer is not this one, if I fail to reject, I guess faculty are working 11 hours statistically. 10 hours is not different than 11. Another way to write it, and you'll see this in the textbook, there's not enough evidence that the mean is not 11 hours. That sounds funny. I use the word not twice. If I say not, that's a double negative. That means it is 11 hours. There's not enough evidence that the mean is not 11 hours. So that, again, that I reversed it. That's just like saying the mean is 11 hours. So why don't I just say that? Okay, so ultimately you can, if you want to, I'm okay with it. But in statistics world, the hardcore statisticians will be like, hey, that's wrong. You can't do that. But it means the same thing, right? I guess statistically the mean is 11 hours. I failed to reject. If I do this as type 1 error, why would it be a type 1 error? Or, I'm sorry, a type 2 error. Whenever you fail to reject this type 2 error, there could be a mistake. I only asked 8 faculty, how long are they working for? How many faculty are on campus? Hundreds, right? 8. That's not very close to hundreds. So I probably need a bigger sample size to get a more accurate measurement of how many hours per week faculty are working. I didn't write it down in words right there, but I mentioned it. Step 3, what it would be. Again, fail to reject, p-value is greater than 0.05. Not enough evidence that there's a difference in the number of hours faculty are working. They use the Z critical value. I guess I could draw a picture of this. So visual, need a visual here. Normal distribution. 11 hours is right here, right in the middle. The mean is 11 hours. So where is 10.05 at? That's one standard deviation below the mean. One standard deviation, this is two deviations, 10.08 is right about here. Or 10.05. This is a t-score of 0, this is a t-score of negative 1.08. Anything over here, this is a two-tailed test, anything over here, over there, will tell us to reject. And again, that's called a rejection region. So if this is the rejection region out here in the middle, I just call this the fail to reject region. Anything in here, fail to reject. Anything out here means reject. So I'm just playing the critical value into this. The T critical value is where we draw that line. Anything below that negative T critical value or this positive T critical value is where we will reject. So I'm just gonna look that up real quick, just for the sake of understanding. Using the T table. The sample size was 8. So I go to 7 degrees of freedom. This is a two-tail alpha and 0.01. So I go to two tails and I go to 0.01, 3.499. So this T critical value is 3.499. And that's something that they asked originally, negative 3.499. So that's kind of a picture of what's happening in the normal distribution curve. And remember when I taught normal distributions in chapter 5, I mentioned this is like the foundation of everything we do in this class with understanding the normal distribution curve. So again, kind of a picture of what rejection regions are all about. So some people are okay with that because they're like, I'm a visual person. But again, I think p-value is much easier because all we have to do is pop it into the calculator, press calculate. Voila, we got a p-value. And that's what we're making our decisions on. All right, cool. Any others? Okay. So the question was. 7.2, number 36. I already know that this is going to be a z-test because it's from 7.2. I think it's going to be. If you're given population standard deviation, you do the z-test. If you're not, you do the t-test. So right here it says population standard deviation is $7,800. The only problem with this is that they give us data. So it's going to take me probably a few minutes to calculate the mean and standard deviation. I could enter the data into the calculator and I could find the mean and standard deviation. Or I could do a t-test and choose. The first question is, do you have data or do you have stats? I could choose stats. Then I have stats. Let me see if I can find the sample mean and sample standard deviation. No. I don't see it anywhere. So let's go right to hypothesis. It says advertising executives in Denver is more than the national average of 67,800. So that's the national average, 67,800. Do Denver executives make more than the national average here in Denver? $67,800. They took a sample of 21 account executives in Denver. Assumed population standard deviation normally distributed, $7,800. Okay, in order to get the z-score, again, I know it's a z-score because they gave us population standard deviation. Get our Z statistic. Again, this says A, B, C, D, E. In part B, find the standardized test statistic. So in these problems, they didn't even ask you to find the Z critical value. It says find the P value. And we can do that with every hypothesis test that we do. We could find the P value. Let me see if I can find the Z and the P value in here without punching all those numbers into a list in the calculator. It's going to take some time. The test statistic is 0.06 and P value is 0.4761. All right. That's pretty much all the calculations that we need. Step 2 is where we do the calculations. Again, as a Z, even though they give us 21 account executives. Okay, I'm thinking advertising account executives. How many? You're not going to have 30 or 40 or 50 account executives. That's quite a bit of people in that field. There's not that many people in that field. So it's going to be a small sample. We use P value. Just like previous problem, P value is greater than 0.05, fail to reject. Not enough evidence that account executives in Colorado make more than 67,800. Or there's not enough evidence account executives are making more than the national average. So if you're an account executive and you're like, oh, move to Colorado, move to Denver, you make more money in Denver than California. Do some research, collect some data. How much money are they making? Nice. So we did a 7.2, we did a 7.3, we did a 7.4, and that's what the quiz is on. So that's cool. We got them all figured out there. Any others? All right. What I want to do is take a vote right now. What do you want to do? Do you want to take quiz number 8 now? So it's going to take probably like an hour to 2 hours. So we're going to sit there and work for 2 hours till probably about 8 o'clock. We're going to be here till like 9:30 tonight. If you take the quiz now and then I teach, okay? Or I could teach now 8.1, 8.2. It's more of the same. You get a Z score and a P value and you reject or fail to reject. Okay, so it's more of the same of what we've been doing. So we can do that, get notes on that, and then take quiz number 8 on our own. You can all go home and take quiz number 8, or you can stay here and take quiz number 8, but do quiz number 8 at the end. So what do you think? Take quiz number 8 now or take quiz number 8 later?
Will it still be due today?
Yeah, I still do today. Yeah. So raise your hand if you would like to take quiz number 8 right now. Okay. Unanimous. Unanimous. Even everyone online, it says later. All right. Yeah. There we go. So one cool thing is it's not all brand new stuff. It's not brand new, more of the same. Okay, that's why I kind of dig chapter 7, chapter 8. They flow together. They really work together here. Let's do it. 8.3 is a little different. But that's going to be next week. We'll get to 8.3. Oh, and another thing is I was thinking next week, the test is scheduled for Wednesday, but I don't have any new instruction for Wednesday. So next Wednesday, the test is that day. So I could do the same thing. I could come in and do review like this for like 30 minutes and then take the test. Or we could just say, we don't even need to come in that day. What do you think? On Wednesday next week? You guys want to come in on Wednesday next week, the class? You want to take it somewhere else? Is that okay?
Yeah.
Okay. Yeah, we'll do that. So there we cancel class Wednesday. The exam, 7 and 8. Is that good for you guys online? Yeah, we got a couple people on there. Yes, they're saying yes. So next Wednesday, I'll send reminders, I'll send the email, and I'll let you know Monday and Tuesday also that there won't be class on Wednesday. So that leaves quiz number 9, I believe. Quiz number 9 is on this chapter 8 stuff. So I'm gonna teach chapter 8 a little bit today, a little bit on Monday, a little bit on Tuesday. So I don't remember if there's room for, we got a quiz on this, quiz number 9. Looks like that's gonna be on Tuesday. And I think it's good to take quizzes because quizzes will help you understand things. When you do things wrong on the quiz, then you learn from it, give feedback. You're like, oh, that's how you do it. I remember when I was a student, right after the test, I got feedback and I was like, I didn't even know that. I wish I knew that before I took the test. I didn't get much feedback when I was a student, if I recall correctly. I got feedback after the test. So I'm trying to give you feedback before the test. All right, here we go. 8.1, watch this. 8.1 is called we're gonna do means. So 8.1 is called a 2-sample test for means given standard deviation. 8.2 is a 2-sample test for means when you're not given population standard deviation. So kind of the same thing we just did. So this is called a 2-sample. And I like to use the calculator 2-sample z-test. Called a 2-sample t-test. What's the difference? Well, if you know the standard deviation, then you're gonna do a 2-sample, you're gonna do the z-test. That's when you know standard deviation. Standard deviation is known. 2-sample t-test, well, that's the other one. That's when standard deviation is not known. Just like 1-sample t-test, or just a t-test, you don't know standard deviation. Just a z-test, number 1, is just called a z-test. That's when you do know population standard deviation. Population standard deviation. Okay. So again, I could get into the formula and all these other things, but again, the calculator does most things for us. One cool thing about doing 2-sample testing is very realistic. Okay, so this is a 1-sample test, not that common. We're comparing a mean to a population. For example, if I take a sample again of students here and I look at GPA, and the average GPA of you in this class is 2.0, and the average GPA of everybody 3.0, then I'm really like, oh gosh, I'm a terrible teacher, right? Then I'm not doing good. I had this happen with the AP test. The average AP score this year was about 2.5. My students, the average AP score was a 1.5. So I did really bad this year. Okay. Or my students did really bad. That means I did bad. Reflects on me. So I can take a value, take one value, compare it to a population. That's what a z-test is. That's what a t-test is. Now we're going to compare two things. So in 8.1, we're going to compare two means using a z-score. So a z-score goes like this: z equals some value minus the mean, or they actually use the word estimate. They're going to take an estimate of a population, subtract the population mean, and divide by a standard deviation. What a z-score does. So when you do a 2-sample z-test, when we compare two means, we're comparing two different things, like two different groups. Okay, again, this is pretty common. So I could take my second period class and my third period class. I can take my Monday, Wednesday class and compare it to my Tuesday, Thursday class. Let's compare this the averages from those two classes. Monday, Wednesday class, they got 80% on average. Tuesday, Thursday class, they got 75%. Is 80% much greater than 75? Maybe. Okay, it depends on sample size, depends on standard deviation, but I'm comparing two things. Okay, let's compare those two groups. This is done a lot with different groups like genders, like comparing different grades for gender groups, right? So we have different groups, we can compare their GPAs. We can compare their average scores. All right, so those scores, we're gonna compare them. Is one group doing better than another group? Okay. We can do this with percentages, we can do this with means. If I give a population standard deviation, the formula looks like this. Again, I'm gonna avoid just doing this whole thing by hand. I'm gonna calculate and compare two means. Divided by standard deviation 1 squared over n1. I can show you where all this comes from. I can derive it for you. That would be a lot of math stuff. That's the actual formula. If you go into the textbook, you won't see this very clearly, because they do this and then they do standard deviation 1 minus standard deviation 2, and then over here they say, oh, there's a formula for those two things, and then you got to plug it in. Okay, here's what's cool about formula is that when we do our hypothesis, when we write our hypothesis statement, we assume that these two things are 0. Like if I'm comparing two groups again, if I'm comparing two GPAs for two different groups. Okay. GPA for females at Hancock College is 3.0. The average GPA for males at Hancock is 2.5. If we subtract those two numbers, I get 0.5. If you subtract those two numbers and get 0, that means there's no difference. If one group is 3.0 and the other group is 3.0, that's no difference. 3.0 minus 3.0 is 0. So this is always assumed right here. This is equals to 0. So in the formula, I don't even need to write it. U1 minus U2 is 0. So x bar 1 minus x bar 2 minus 0 is just x bar 1 minus x bar 2. I don't even need it. Okay, in the book they write it, but it's not needed because it's 0. So that's the z-score formula. Our hypothesis, when we do a statistical test for two samples, when we compare two means, the hypothesis is going to look slightly different. Let's calculate a z-score. Once you get a z-score, then you get a p-value, look it up in the table. Been there, done that. Okay. I'm going to write the hypothesis. We have 3 different ones that we can write. They're all on page 420. I'll write them right over here. Either the two means are equal or two means are not equal. Either the two means are bigger than or at least or less than each other. Or the third option would be greater than. Okay, so really, these two things, we could do either one. So it's really important what we call mu1 and mu2. Most students will just take the first data that you get, the very first thing that you see. Oh, I'm going to call that number 1. And I'm going to call the other data number 2. But if I switch mu2 and mu1, then I got to do this formula right here. Okay. So essentially I could use either formula if I got a less than or a greater than. If one value is greater than or one value is less than. Again, all of those are on page 420. So that's how we write our hypothesis. How do I know which one to use? How do I know which one to use? if the college president believes that females have a higher GPA than males. Higher, bigger, greater. So what am I gonna do? I'm gonna say mu1, I'm gonna use this one right here. I think the GPA of females is greater than males. mu1 is female GPAs, all female GPAs in the college. mu2 is going to be male GPA. I'm gonna compare the groups. Decide, is there a difference? Okay, is one bigger than the other? So what I was just saying in words, this is kind of hard to wrap your brain around when you first see it. I could have said, it is female GPA higher than males, okay, and that's kind of a note. There's more females in college than males. I could say that just by looking in this room. We have 2 males in this entire class, 23 students. More females go to college than males. Our female GPA is higher than male GPAs. That's the same exact saying as male GPA is lower than female GPA. Does that make sense? I could have used this one if mu1 is male and mu2 is female. This means females have a higher score than males. This would mean males have a lower score than females. So really I could use either one, and we'll do an example of that here in a minute. So the ultimate goal, get a Z-score. From the Z-score, get a p-value. Get a p-value, use a standard normal table. If p-value is below 0.05, there's evidence to reject. HO. P-value is greater than 0.05. Not enough evidence to reject. Oh, we're doing the same stuff. So that's why I said this is kind of the same stuff. We modified the hypothesis a little bit. We modified the Z-score calculation a little bit. We're still subtracting 2 things and divided by standard deviation, finding is there a difference or is there no difference? Okay, so I'm going to show both methods by using example 3. So if you're in your book, go to example 3 on page 423. I want to walk you through it first, and then I'm going to have you do it on the calculator. They gave you calculator steps. They didn't really show the solution. So I'm going to walk you through it first. Okay, how to do it by hand, how to write the hypothesis, and do all these things. Okay, I'm going to decide which one I'm going to use. A travel agency claims that the average daily cost of meals and lodging for vacation in Texas is less than the average daily cost in Virginia. There we go. One is less than the other. Does that make sense? Vacation in Texas. Well, now it's more. A friend of mine has a house in Texas. He's like, he bought a house here and he has a house in Texas, in Austin. He's like, this house in Texas is worth more than this house there. You know, all these people are like, I'm moving to Texas, it's cheaper. And not so fast. He just told me this like a month ago. So not cheaper in Texas. Well, it depends where you live, but everyone's moving to Texas, therefore house prices go up. So his house in Texas is worth more than his California house in Santa Maria, California. Pretty interesting. Anyways, Texas is less. I'm gonna write my hypothesis. That's the hypothesis. Does it cost less? Does what would you call that? Daily cost of meals and lodging. So I'm just call that travel cost. Okay. So I'm gonna write it in words and symbols. Does travel in Texas cost less than travel in Virginia? Question mark. I know something about Virginia. Virginia is where a lot of people live that work for the government, right? Pentagon, Washington DC, a lot of senators, a lot of House of Representatives, people live in that area. And I'm sure housing and lodging is very expensive, a lot of museums there. So I know a little bit about Virginia, even though I've never been there. I'm gonna write this in symbols now. I gotta need an HO and an HA. I need a mu1 and a mu2. Okay, what should we call one? Number one. Which one do you want? Texas? Okay, so number one is gonna be Texas. Texas came first. So the cost in Texas is less than the cost in Virginia. Does that make sense? So less than. I'm gonna use our second set of hypothesis. Again, that's on page 420. So one is less than the other. mu1 is less than mu2. Or mu1 is greater than or equal to mu2. So I gotta define this is called defining your variable. What is mu1? So I gotta make sure I do this. mu1 is cost of travel in Texas. I'm just abbreviating. Again, if I switch those, I could do another test. I could say it costs more in Virginia than in Texas. It does the same thing, satisfy the same hypothesis. Sometimes you might see this. Instead of writing ones and twos, like we have over there, that's just 1 and 2 are just generic symbols. I could use a letter to represent Texas and Virginia. So if mu1 is Texas, I'm gonna put a T there for Texas. mu2 is Virginia, I'm gonna put a V there. So that's something that happens as well, especially if you're in the real world and you're doing or working in statistics in the field, right? You would probably want to do something like that. Cost less to go. I need the data now. Texas, $234. Virginia, $240. It's 234 less than 240. So I said use your logic brain. And I know you have logic brains because you're in college. If you weren't in college, you probably would not. $234 is that less than 240. 34 by $6. Okay, you're talking about hotel, food, expenses. Difference is $6. I don't think that's much of a difference to you. $6, not much of a difference. Starbucks coffee costs $6. I mean, come on, right? So I'm gonna do the calculation now. You don't have to do this. I'm gonna show you how to do it by calculator. It's 234 less than 240. Standard deviation for Texas was $19. 19 squared over square root of 25. There are 25 people sampled in Texas and 24. All this stuff is given to us, and I'm just plugging. It's just a plug-in stuff. And this is why I said you don't actually have to do it by hand because I'm just plugging in the values, but I'm just doing it for show and tell. All right. I'm gonna do that on my calculator now. I'm gonna come up with the different. It's gonna be a negative z-score. 234 is below 240. Less than. I want Texas to be less than. Less than means negative. Less than 0 is a negative number. If it said greater than, I'm taking positive z-score. So I'm gonna do the calculation. I'm gonna do all this first. I'm gonna do the denominator first. So I don't screw things up. 19 squared divided by 25 plus 24 squared divided by 20, 43. All right, so it shows, I was just doing the calculations, I was getting confused, so sorry for the pause. Page 423. This is on the calculator, it's called a test. What kind of test is it? It's called a two sample z-test. And why is it a two sample z-test? Because they gave us the standard deviations, which were 19 and 24. I have stats. Okay, it's kind of weird. I don't like the order that they do this. They put standard deviation first, which is weird. 19. Standard deviation 2 is 24. First mean, 234. First sample size, 25. X bar 2 is 240, and 2 is 20. Not equals, less than, greater than. Oh, it's a less than. It's a less than. Calculate. There we go, negative 0.91. P-value. Okay, that's what we're looking for. We're looking for this big number called the p-value, 0.18. It looks like I got the same numbers that they got on page 423. That makes sense? Step 3. Looks like we're going to fail to reject, same as the previous 3 problems we did. We're going to fail to reject. P-value is greater than 0.05. There's not enough evidence that traveling in Texas is less than traveling in Virginia. Like I said, $6, not much of a difference between those two things. Cost of a Starbucks coffee. If you switch all of your standard deviations, your means, if I switch it around, call this number 1 and that one number 2 and choose a greater than, I will get a positive z-score, a positive 0.91. And I do a right tail test, I get the same p-value. You get the same p-value if you do a right tail test. 0.18. Example 2 is a two-tail test. It's 4,000 debit card debt or credit card debt in California and Illinois. California has Los Angeles, Illinois has Chicago, big cities. $4,777. Is that different than $4,866? Get a z-score of negative 0.82. And that p-value is probably going to be like 0.7 or 0.8, something like that. Fail to reject. Okay, so on example 2 is the fail to reject as well. All right, cool. So like I mentioned, a lot of the same stuff that we've been doing. We just modified the hypothesis. We're modifying the calculation, but again, we can avoid that by doing a two sample z-test number 3 on the calculator. Yay. All right. So I'm going to give you plenty of time to work on 8.1. Not too much time though. I got the problem set right up here. 15 through 23 odd. 5 problems. So the homework's 5 problem. Problem sets are getting a lot shorter. Okay, so I'll get into a couple of those. We're only going to go for about 30 minutes. I want to give you time to be able to work on the quiz later. So I'm going to give you like 30 minutes. We'll reconvene at 7. And then we'll go on to 8.2. So example 1 on page 430. So let's go to example 1. Page 430. And it's a 2 sample t-test. How do I know? Because standard deviation is sample standard deviation. Now they give us S. It's a two sample t-test. The standard deviation is gonna, population standard deviation is gonna be a no. We're gonna use S. So here we go. The results of the state math test for random samples of students taught by two different teachers are given. Can you conclude there is a difference in the mean math test scores for the students of the two teachers? Okay, so we got two teachers. We got the average math scores for the two teachers. We want to know, is there a difference? Maybe one teacher has better methods than the other teacher. I don't know. Is there a difference? There's no less than, there's no greater than, so we're just gonna use that one right there. There's your hypothesis. And again, it shows right there on example 1, halfway down, where the solution is at. So we got our hypothesis. Is there a difference in math scores? So again, use our logic brain, 473 and 459. Is 473 different than 459? Yeah, I think so. 473 is kind of bigger than 459, right? That's the difference of like 14 points, 15 points. Okay. 473 and 459. It's on the left side in the margin. Let's do this on a calculator. Go to the calculator. Again, all these calculations, we have two formulas. We're going to pool our data or we're not going to pool our data. So we have to determine which one it is. Stat, test, two sample t-test. We don't have data. I like t-test better because it gives x1, s1, n1. Exact same order they give it to us. 473. S 39.7 and 8. X bar 2, 459, S 24.5 and 18. Enter all my data. Not equals, less than, greater than. This is a not equals. We're trying to test if there's a difference between the two scores. And then there's a new question at the very bottom. It says pooled, yes or no? So which one is it going to be? Are we going to pool our data or not pool our data? Which formula are we going to use? Have to read the question. Population variances are not equal. Did we see that? Last sentence. Population variances are not equal. So what are we going to do? Are we going to yes pool or no pool? We're gonna say no. Everybody find that? No, no pool. Calculate. Oh, p-value. There we go. 0.379. P-value. 0.379. Okay. Are we going to reject or fail to reject? Looks like p-value is greater than 0.05. We are going to fail to reject. There's not enough evidence that there's a difference in the math teachers, students' test scores. Not enough evidence of a difference between test scores for the teachers. Even though I thought 473 was bigger than 459, that's only a difference of 14 points. Not significant. That's why it's called a test of significance, not a significant difference. Cool. Okay, what if I went back and I chose, this is what I was just stating. What if I said, I mistakenly said, yes, pool data. The p-value is 0.279. Okay, so what's this pool business anyways? All that tells us population variances are equal. That's kind of unrealistic assumption to make. This is unrealistic. Population variances are equal.
No one pooled them.
Because it said in the question, variances are not equal. But we said, do not pool your data. There's another thing that they give us. I did talk about it. It's called degrees of freedom. Do you see the DF there? So degrees of freedom is 9.45. Degrees of freedom 9.45 are close to 10. The degrees of freedom formula for t-testing is the worst formula that you'll see. You can look it up. It's not in our book. I've seen it in other statistics books. But the degrees of freedom formula for two samples is pretty crazy. You can Google it. It's a pretty fun one. It has n's and s's and squaring and square rooting and all kinds of stuff. Looks kind of like that in a way. But the calculator calculates it for us. So usually it's degrees of freedom would have been 7. If I take the smaller sample size, which is 8, smaller sample size is 8 and subtract 1, I get 7. Or I do this, 7 or add the two sample sizes together. 8 plus 18 is 26, subtract 2 is 24. But the actual degrees of freedom the calculator uses is in between those two numbers. Cool. So this is just a new addition to what we've been doing, pooling and not pooling. So an example 1 is an example of variances not being equal. So we're going to use that p-value. Either way, 0.279, 0.379, they tell us the same thing. They both tell us to fail to reject. They're both bigger than 0.05. Example 2, page 431. Okay, let's read the question. A manufacturer claims that the mean operating cost per mile of its sedans is less than that of the leading competitor. Less than. So in example 2, we're going to use less than. Right down purple. The operating cost per mile is less than its competitor. Therefore, you need a car warranty. That was my joke of the day. Nobody laughed. Okay, that's tough crap. You conduct a study using 30 randomly selected sedans from the manufacturer and 32 from the leading competitor. The results are shown at the left. So we have all the data there. All the data is given. Assume population variances are equal. Everybody see that? Population variances are equal. Now we got to do that formula. Well, I'm going to again do it on the calculator. So let's do it on the calculator. Stat test 2 sample t-test. X bar 1.52, S1 0.05, N1 30. X bar 2.55, S2 0.07, and 232. Less than is 52 cents less than 55 cents. Not really much of a difference between those two numbers I'm thinking right now. Cool. Yes or no? Looks like a yes. Calculate. E-value. 0.029. Okay, this problem has an alpha of 0.05. Like I said right there. P-value is 0.05, or alpha is 0.05. 0.029 is less than 0.05. We're going to reject. There's evidence that the operating cost for sedans is less than their competitors. For the manufacturer, cost is less than the competitor cost. Again, if we pool our data, 0.029. If we did not pool our data, my p-value would be, let me look real quick. Say no. P-value 0.028. If I said no pooling, we still have the same result. We still reject HO. So again, in the big picture, it doesn't really matter if you say pool or not pool. It just does a little bit different calculation for us. But at the end result, we still got to reject or fail to reject. We're still going to pick one or the other. Okay. We're going to say fail to reject. There's evidence B1 is less than B2. All right, great. 3 through 12, 14, 21. So again, try to work for about 30 minutes or so, work on some problems. Try to get some idea of where you're going, or you can start on the quiz. If you want to, quiz number 8. So you don't have to be here.